All right, buckle up, everybody, because today we're diving headfirst into a physics paper that's, well, it's making some waves. Let's just say that.
Definitely making
It's
waves.
called A Geometric Unification of Fundamental Interactions and Particle Properties. Oh, and the subtitle, it's got a subtitle, The Theory of General Singularity.
Yeah, so it's trying to do something that physicists have been, kind of chasing after for centuries now.
Yeah, the Holy Grail.
Basically trying to unify all the fundamental forces, and not just those, but the particle properties too, all within one framework.
Right.
And, get this, it's all based on geometry.
Geometry.
I mean, that's pretty wild.
Yeah, it's an incredibly ambitious theory for sure. It takes, that idea that Einstein had that gravity is like curved space-time
Yeah.
and just takes it so much further.
Yeah, I mean, color me intrigued, but also maybe a little intimidated. We're talking about unifying gravity, electromagnetism, the weak force, the strong force,
Right.
like all of them.
All of them.
It just seems almost impossible, doesn't it? Well, that's kind of what makes it so fascinating to look at. This theory, it's suggesting that all these forces that seem so different, and even the properties of particles themselves, it could all just come down to the geometry of some higher dimensional space.
Okay, wait, hold on a second. Higher dimensions. That sounds like, I don't know, what, something out of Star Trek.
It might sound a little strange at first, but the idea of extra dimensions has been around in physics, well, for quite a while now.
Really?
Yeah. Think of it like this, okay? Imagine you've got a tightrope walker up on a high wire.
Okay, got it.
From their perspective, they can only move, forward or backward along the rope, just one dimension, right?
Right, right.
But then imagine like a little ant crawling on that same rope.
Okay, I can picture that.
To that ant, there's another whole dimension, right? The circumference of the rope itself.
Oh, I see. So the ant experiences this extra dimension that the tightrope walker is totally oblivious to.
Exactly. And that's kind of how it could be with our universe. We're like the tightrope walker stuck in our four dimensions.
Mhm. Three of space, one of time, right?
Yep, exactly. But this theory is saying that our four-dimensional space-time,
Mhm.
it might just be a tiny slice of some much bigger, higher dimensional space. These extra dimensions, they're all curled up, so small we can't even see them directly. But it's their geometric properties that could be giving rise to all the forces and particles we see.
Okay, I think I'm starting to get it. So instead of like separate force fields, we've got this one big multi-dimensional space, and it's the way it's shaped that creates everything.
That's the basic idea.
Yeah.
The way it's shaped, that's where things get even more interesting. It's not just the curvature of space-time, like in Einstein's theory of gravity.
Mm.
It's also something called torsion.
Torsion. Now that's a new one for me.
Okay, so imagine you've got like a flat sheet of paper
All right.
and you twist it.
Yeah, like twisting a towel or something.
Exactly. That twisting, that's basically analogous to torsion. It's this way that space-time can be twisted on top of being curved.
Okay, I think I can visualize that. But how does this torsion, how does it play a role in all of this? Unifying forces and particles.
Well, this theory is saying that torsion is actually what gives particles their spin.
Wait, really? So the way space-time is twisted determines whether a particle is, say, an electron or a quark.
Exactly. And it goes even further than that. Torsion, it could also help explain some of the weirder, more mysterious properties we see with particles, like the masses of neutrinos,
Neutrinos, you mean those super elusive particles that barely interact with anything?
the very same.
Okay, now I'm all ears. Tell me, how does torsion come into play there?
Well, there's this mechanism called Majorana mass generation, which basically means that neutrinos could actually be their own antiparticles.
What?
Yeah. And this is all allowed because of the way torsion affects space-time. It leads to these particles having these incredibly tiny masses.
Wow. Okay, torsion is sounding a lot more important than I initially thought.
It's a big deal in this theory. And it gets even weirder when we start talking about, black holes.
Black holes. How do those even fit into all of this geometry talk?
Well, the theory suggests that black holes, these super dense objects with insane gravity, they're also described as these geometric entities called general singularities.
Hold on, so you're saying that tiny particles and massive black holes are basically just different expressions of the same geometric principle?
That's the wild idea at the heart of all of this. And it could potentially solve one of the biggest mysteries in physics, which is the whole singularity thing. Instead of being these points of infinite density where our current theories break down, singularities become fundamental geometric structures in this framework.
Okay, I gotta admit, that's pretty mind-blowing stuff. But as elegant as this all sounds, is there any way to actually test these ideas? Can we even observe this higher dimensional geometry and its effects on particles and black holes?
That's where things get really exciting. This theory, it's not just some mathematical daydream. It actually makes testable predictions.
Okay, now we're talking. Tell me more about these predictions. What should we be looking for?
Well, let's start with those extra dimensions we were talking about. So those extra dimensions, they're not just some like abstract mathematical idea. They could actually have observable effects.
Okay, like what? Give me an example.
One of the predictions is something called Kaluza-Klein resonances.
Kaluza-Klein resonances.
Yeah, it's like you could think of it as an echo of those extra dimensions, but in the world of particle physics.
Okay, I'm listening. Break it down for me. What are Kaluza-Klein resonances, and how do they connect to these extra dimensions?
All right, so imagine like a guitar string.
Okay.
When you pluck it, it vibrates at a certain frequency, right? That makes a certain note.
Right. Right.
But it can also vibrate at higher frequencies. Those are called harmonics. They make higher notes.
Gotcha. So how does that connect to, particles and extra dimensions?
Well, in this theory, the extra dimensions, they're like those guitar strings. They can vibrate at different frequencies, or you could say energy levels.
Okay.
And those vibrations, they show up as particles with specific masses. So Kaluza-Klein resonances, they're like heavier versions of known particles. They correspond to higher vibrations of those extra dimensions.
So you're saying if we smash particles together with enough energy, like in a collider, we might create these heavier particles, and that would be evidence for extra dimensions.
Exactly. It's like hitting that guitar string harder to make those higher harmonics. And the cool thing is, the theory actually gives us clues about where we might find these Kaluza-Klein resonances, like what energy scales we should be looking at based on the size and geometry of the extra dimensions.
So there are specific experiments we could actually do to find these particles.
Oh, yeah, absolutely. Experiments at the Large Hadron Collider, for example, they could potentially produce these Kaluza-Klein particles.
And finding them would be huge, right?
Oh, it would be a massive breakthrough. It would be strong evidence for the existence of extra dimensions, like really strong evidence.
Okay, so that's one potential piece of evidence. What about torsion? You mentioned earlier it could have observable effects too.
Yeah. Yeah, torsion could definitely leave its mark on particle interactions.
How so?
Well, it's more subtle than these Kaluza-Klein resonances, but it could show up as tiny deviations from what the standard model of particle physics predicts.
The standard model, that's our current best theory of how particles work, right?
Exactly, and it's been incredibly successful. But the thing is, it doesn't include torsion.
Okay.
This new theory, it predicts that torsion could cause slight shifts in, like, particle decay rates or the probability of certain interactions happening.
So we'd need super precise experiments to even detect those tiny differences.
You got it. But the good news is, experimental particle physics is getting more and more precise all the time.
That's good.
There are experiments going on right now and more planned for the future that could actually reach the level of sensitivity we need to see these subtle torsion effects.
So I might have to wait a bit for those results, but the idea of actually measuring the influence of torsion, that's pretty wild.
It is. And it's not just particle physics where we might find evidence. Cosmology and astrophysics, they offer some really interesting possibilities too.
Oh, interesting. Tell me, what could we observe on a cosmic scale?
Well, remember we were talking about black holes as general singularities.
Yeah.
That could really change how they behave.
Okay, how so? How could black holes act differently in this theory?
The way they interact with the stuff around them, matter and energy, it might be affected by the geometry of those extra dimensions and the presence of torsion. It's like, imagine that tightrope walker again. But suddenly they realize they're not just walking on a line, they're walking on a rope with a certain thickness and texture.
So we might see black holes acting in ways that the standard theories don't predict.
Exactly. And these deviations, they could show up in a bunch of ways. How they gobble up matter, the gravitational waves they emit, even how they mess with the motion of nearby stars.
So by studying black holes carefully, we could find clues about the underlying geometry of space-time.
Precisely. And those clues, they're not just limited to black holes. This theory could even affect gravitational waves themselves.
You mean those ripples in space-time caused by massive objects moving around?
Those are the ones, remember we talked about torsion being like twisting space-time?
Yeah.
Well, that twisting, it could actually create extra polarization states for gravitational waves.
Polarization states. Refresh my memory. What are those again?
Okay, picture shaking a rope up and down. The wave travels along the rope vertically, right?
Yeah.
That's one polarization. Now shake it side to side, the wave's polarized horizontally. Gravitational waves, they have polarizations too, but this theory is saying there could be more than the usual two because of torsion.
So we're basically looking for a new way these gravitational waves can wiggle.
Exactly. And future gravitational wave observatories, they might be sensitive enough to actually detect these extra polarizations. It would be another way to test the theory.
This is incredible. We're talking about seeing these tiny effects of extra dimensions and torsion, not just in particle colliders, but by studying black holes and gravitational waves across the universe. It's like this theory is opening up a whole new frontier in physics.
It really is. And we're just scratching the surface here. This theory has implications for, well, pretty much everything, from the behavior of fundamental constants to the very structure of the vacuum itself.
Okay, I'm hooked. Tell me more.
Well, for example, the theory suggests that the strength of fundamental forces, like electromagnetism, they might not be so constant after all. They could vary a little bit over time or in different parts of space because of the changing geometry of those extra dimensions.
So those fundamental constants, maybe they're not so constant after all.
That's right. And scientists are already looking for signs of these variations using super-precise atomic clocks and astronomical observations.
Wow.
Finding evidence of those variations would be another big win for this theory.
This is blowing my mind. What about the vacuum? You mentioned that earlier.
Ah, yes, the vacuum. Often thought of as empty space, but in this theory, it's anything but empty.
Really?
Remember the state matrix we talked about before?
What?
Well, it predicts this whole landscape of possible vacuum configurations, each with different strengths of the fundamental forces.
So the vacuum, it could be more like a dynamic, ever-changing thing, not just a static background.
Exactly. And those changes in the vacuum, they could have huge implications for cosmology. They could influence the expansion rate of the universe or even the formation of galaxies.
This is incredible. We've talked about testable predictions in particle physics, black holes, gravitational waves, fundamental constants, even the vacuum itself. Is there anywhere this theory doesn't have implications?
That's what makes it so compelling, right? It
Because
connects all these seemingly separate areas of physics and gives us this unified view of the universe, a view that's both elegant and profound.
this has been an amazing journey so far, I gotta say. But before we get too carried away with the implications, I think we need a minute to let all of this sink in. When we come back, I'd love to hear your thoughts on what this all means for the future of physics. Okay, so we've gone through some seriously mind-bending ideas here. Extra dimensions, torsion, black holes as geometric entities, the vacuum being this dynamic landscape. It's a lot to take in. But stepping back for a minute, what does it all actually mean? What are the big implications of this theory, if it turns out to be true?
That's the really exciting part, isn't it?
Yeah.
We could be looking at, a total paradigm shift in how we understand the universe.
Right.
Imagine a world where all the forces, all the particles, everything we've been studying for, well, centuries, they're not separate things. They're all just different sides of this same underlying geometric structure.
It's almost like we've been seeing the universe through this, I don't know, this fragmented lens, and now this theory is giving us a way to see the whole picture. Like the interconnectedness of it all.
That's a great way to put it. And this shift in perspective, it could really help us tackle some of the biggest mysteries in physics, the ones that have been stumping us for, decades.
Like the whole problem of unifying quantum mechanics and general relativity. Those two, they seem to describe totally different worlds, right? The super tiny and the massively huge.
Exactly. And trying to bring them together, well, it's led to all sorts of contradictions and paradoxes.
Yeah.
But this geometric theory, it offers a glimmer of hope.
How so?
Well, by describing both particles and black holes as these general singularities, it hints at this deeper connection between the quantum world and the world of gravity.
So instead of having two sets of rules, we could have one unified framework that governs everything, from like the tiniest particles to the largest structures in the universe.
That's the ultimate goal, right? It would be a revolution in physics. A real culmination of centuries of scientific work.
Yeah.
And it wouldn't just be some, intellectual victory either. This kind of unification, it could lead to, profound new insights into the very nature of space, time, reality itself.
So this theory, it's not just about explaining what we already know. It's about opening up whole new avenues of exploration, like pushing the boundaries of what we thought was even possible.
Absolutely. It's like we're upgrading our understanding of the universe to a whole new level. And with that upgrade, Well, a whole new set of possibilities opens up. We might finally be able to crack the mysteries of dark matter, dark energy, understand the origin of the universe in a completely new way, even discover, I don't know, entirely new realms of physics, things we haven't even imagined.
It's almost overwhelming to think about all the potential implications.
It is, isn't it?
But it's incredibly inspiring. It gives you this sense of awe and wonder at the complexity, the beauty of the universe.
That's the power of fundamental science, right? It can change our perspective, challenge our assumptions, and just fill us with this sense of wonder at all the mysteries that are still out there.
This deep dive, it's definitely left me wanting to learn more, to keep exploring and asking questions. And I hope it's done the same for you, our
I
listeners.
think that's a perfect place to wrap things up. The universe is full of mysteries, and trying to understand them, well, that's one of the greatest adventures we can go on.
Couldn't have said it better myself. And thank you for joining us on this incredible journey into the heart of a geometric theory of everything.
It's been a pleasure.
Until next time, keep diving deep.